So as you are likely aware, we're going to look at 3D center of moments, and then we'll put weight on those trusses and see what happens to them. So imagine this, just so that it's something you maybe can picture in your mind as being like a bullet, something like that. And you guys have copies of this from the other day, right? Is that true? I didn't bring extras, so I hope you do. Notice the top of that from your algebra skills, because it's a y and a z squared, although I would have thought it'd be an x and a y or something, but one is squared, one is not. So that actually means that outer surface is a parabola. This also should look like calculus to you in the sense that in calculus, didn't we take kind of a curve like that, a parabolic curve, and then we said, wouldn't that be fun if we rotated it around the x-axis, and then that would create a solid, and that solid we could either find the surface area of it or the volume. So cool. But of course, the center of mass of a two-dimensional object is important, and I guess I would like you to understand, and I'll erase this, but from the other day, if I was looking at an I-beam or something like this would be an easy center of mass. I don't need to even do any math because it's symmetrical in every direction. And so the center of mass would be right there, even though it's three different rectangles and so forth. But does it make sense to you that although, I might have drawn that as a two-dimensional object, that's what's underneath every house is an I-beam. The fact that it just went 3D, I don't have to do a bunch of math. I still know that's the center of mass. Now, maybe it's kind of like an axis or something like that. I mean, all those points continue through the shape, but I know where the center of that mass actually is. And later on, I hope we either get to that this term or perhaps in strength of materials in the spring. When that object wants to bend under weight, because it's not going to be rigid. There's, in a sense, no such thing as anything that's rigid. It's going to bend some. The fact that you know where that center of mass is a really important part of understanding how it's behaving. If it was bending like this, can you see the top fibers crushing together in compression, whereas the bottom fibers are pulling apart? So that center of mass line right there, the top half is under compression and the bottom half is under tension. And that's actually really important. For most things, you just kind of say, oh, well, and make it out of concrete, or you make it out of wood, and some fibers are ripping apart, some fibers are crushing. But just as an example, in the case of a concrete I-beam, which most of our bridges have underneath them now, almost all of them do. Next time you look at the underside of a bridge, you'll see those. What they really do is they just bring them in on a truck, usually at night because it's massive. And they place these things next to each other like this. And then they come back and put form boards between all of these, and then they pour a concrete deck on the top of it. And so all you see is kind of the 6-inch concrete road. The structure underneath it is those concrete I-beams. But what's interesting about concrete, awesome in compression because it's a rock and it doesn't want to crush, terrible in tension. You actually can't use concrete I-beams unless you come back and put something that is good in tension. In the case of concrete, they actually run a piece of rebar through the inside of that because rebar metal is awesome in tension. So that's actually inside there and you just don't see it. So there's a whole technology to that I'd love to talk about, but don't have time right now. So there has to be some kind of a support underneath that. And you may have noticed that drawing we did the other day, it looks something like this. And it had like a big bulbous kind of a deal on the bottom. Looks a little sexual. Then if this up here were wood, if you will, that would make sense. But if this was like a big piece of steel down here, that'd actually be kind of cool. And that would do well if you put it in there the right direction so that the bottom steel part kind of worked in tension. And so again, what's important about why am I saying all this? Because the center of mass is the dividing line between those two things. And so center mass is really important. But notice, even though that I-beam is a three-dimensional object, I don't really have to do anything fancy to find its center of mass. It's entirely based off its two-dimensional cross-section, if you will. But the shape we're looking at, not so lucky. I mean, that's sort of a mathematically defined shape. Just as a side note, if that, I just turned this sideways, but what if this was a circle? So this is like a half circle, at least in terms of its shape. It's like a half sphere, technically, is what you see in a math class. Does it make sense that from the side view, the center of mass is not going to be in the middle vertically because you got more stuff on the bottom than you have on the top, and therefore, this point would have to kind of go down a little bit. So does it make sense? It's kind of not trivial to figure out where that would be. Where would that actually be? I want to say, I doubt any of you have your textbook, but there is a couple of pages in the back of the book that tell you where some of these classic shapes are located, which is kind of interesting. And it, off the top of my head, I want to say this one was also 2/3. Like instead of at the halfway point, it was 2/3 of the way down from the top. And so if you do, yeah, you have yours, look it up. If there are some classic shapes, as circular shapes would be, somebody does the math, just like we did for triangles, and it's like 2/3 of the way over, then we never have to do the calculus again. I would say this question is, I almost want to say largely irrelevant. However, I don't think bullets are made with circles. Do you? I mean, is anybody shooting here much? I'm kind of imagining the bullet to kind of look something like this. It's almost like it goes straight for a while and then it kind of curves at the end. Isn't that what kind of the slug of the bullet looks like? Again, why might you want to know the center of mass of that shape? Because you may understand a little bit about guns, but a lot of guns have rifling on the inside of the barrel, so that when just like a quarterback throws a pass, you got to get that thing spinning or it starts to wobble like a duck. So you want it spinning and then it'll kind of fly straight. So you rifle it so that when the bullet comes out of the gun, it starts to spin and then it shoots through the air. Of course, if it's flipping, it's going to get a lot of wind resistance. It's not going to fly straight. It's not going to hit its target. So does it make sense though, if it was rotating, the center of mass would be the point around which it's rotating. And so you can picture that that's kind of a valuable skill. So I do see this question being, well, a parabolic top, if you will, being, my first reaction is like, who cares? Who would ever need to know that? But who knows? Maybe a bullet is parabolic. Maybe that is a better shape. Maybe that cuts through the wind better. If something was truly round on the end, doesn't it feel like it'd have more resistance than, if it was kind of a little bit more pointed like that? It feels like it would shoot through the air a little bit better. So, obviously the big question is just how do you find that center of mass? Was there anything in the book about that, or did you?
I don't see anything.
Let me have a look. This. Can I show you this? This is. I think I have to unshare this screen to do it. There we go. It's been a long time since I've used this. So let's just look at a couple of things really quick, just because it's interesting that they're in the back of the book. Notice this is talking about geometric properties of line and area elements. And so notice here's a literal half circle. Like this is not a sphere, it's just literally a flat half of a circle. So notice it says right here that that distance up, let's see, does it tell us what that distance is? Notice it says there's a formula for how to find C, which is the centroid location. Notice that language at the top, the centroid location. So notice some of these interesting shapes. So I'm looking at this half circle and notice it says, wow, that's a pretty complicated little formula. In other words, it's not just 2/3 in a sense like I guessed. It's actually 4r/3 pi. That's how far it is up from the bottom. Isn't that kind of surprising? Does it make sense we could have figured that out ourselves from calculus if we kind of decided to go down that road? Since that came up, extra credit if you want to tackle that, but don't tackle it unless you get it right, meaning have me help you if it doesn't work. So if you wanted to actually do it with r in it, remember you would treat r like a constant. So although that says 4r, like r is a letter, yes, that's a variable, but you're treating it like a constant. See if you could reproduce that. Of course, doesn't the center of a circle seem rather trivial? Like, did we need to know that it was at the center? Like, why did they include that? I don't know. Center of a rectangle, duh, right in the middle from both directions. Notice over here, though, there's some stuff that kind of looks similar to our book assignment. Like, didn't we have a couple of questions like this on Tuesday where this is saying it's 3/4 of the way over, whereas this over here is 3/10 of the way up that side. And notice they're saying this is parabolic. In other words, that curve is a parabola. So actually that makes me think, I wonder if I could have cheated to get those, because didn't we have 2 parabolas for what we did in class? This is like, oh, you mean there's a pattern to this? I don't have to actually do calculus. We could have found a pattern that told us this. Again, if you have time on your hands and you want to prove, wow, it's actually 3/4 of the way over and 3/10 of the way up. Like, could you prove that? Could you be the one that built that? Could you be the one that made that? That might be worth doing. And then down here, hey, that's kind of similar to what we're doing right now. Like, this is a parabolic, and notice it's an area though. Again, it's not 3D. I don't know if you can appreciate that it'd be different, but as soon as it's 3D, that means there's even going to be more stuff on the bottom edge. So probably if this is a 3D parabola like we're about to do, I don't think it's going to be the same. But notice 2/5. Isn't that interesting? Not 2/3, 2/5. Yet it is kind of a nice fraction. Isn't that kind of interesting? So it's 2/5 of the way up for a flat parabola. What about 3D stuff? Again, does a sphere seem trivial? Notice over here, instead of C for centroid, they called it the center of gravity. So they put G. So it's like it's in the center of a sphere. Well, duh. What about a cylinder? Hey, look, it's halfway from the top and duh. It's like there's some of these that are, I see why they put them in here, but would you agree a cone, not so trivial now because there's more on the bottom than there is on the top. So this seems to be saying it's 1/4 of the height up. It's 1/4 of the way up. Again, is that interesting? I would have thought maybe it was a third, or a second ago we had something that was 2/5, and yet this one is a nice fraction, but it's 1/4. What about a sphere? Notice it's 3/8 off the bottom. Isn't that kind of weird that we just have 4ths and 5ths and quarters and 8ths? So this is similar to what we're about to do, but notice interestingly, there's no paraboloid. Like, if my goal was just to be an engineer and like get done with this, the problem I'm about to do, I guess I don't get any help. There probably is an answer to it. It just isn't in the book. I bet if you Google searched, you could probably find a formula for that someplace. Maybe this book is just not that complex. But that's kind of cool. And then just because I'm staring at it, notice this one's kind of cool. It's a ring, you know, like a wedding ring, yet the center of mass or the center of gravity is not anywhere on the ring. It's in space. We talked about that with the chair. The center of gravity actually does not have to be in the shape. If it's hollow, it won't be. And if you look at these desks, you can probably appreciate the center of mass is underneath the desk somewhere because the legs are adding weight to it. But again, it'd be kind of fun if I could just take one of these desks and throw it across the room and we filmed it in slow motion, because you've got to actually watch it rotating around the center of gravity. I mean, you could just flip it in the air and figure out where the center of gravity is and not even have to do all the math. So it's just kind of an interesting concept. So anyway.
On the 3rd floor, we could just-
I know. You guys want to get outside with the camera? We'll break the window and check one out.
It'd be kind of interesting if you like threw a bunch of items just to a regular person and then maybe made a few rotate not on the center of axis and see if they notice like something's off. Not like drastically, but like
Yeah.
just like put the center axis like somewhere else and have it rotate
Yeah.
and see if they're like that looks
Like you
weird.
threw it to him and it was spinning around this
Yeah.
point the whole time.
If the person was just like, that seems really weird. Like, why are they doing that?
I think about this a lot because this is worth watching even if you don't mountain bike, but there's a YouTube kind of a thing that pops up every week called a mountain bike, what is it called? Friday Fails. So basically people constantly video each other doing things. And so it's like, hey, I'm going to jump this, video me. And that's great if everything goes well, but if they crash and it's kind of a funny one, then they send it to the YouTube and then they just put this compilation of crash videos together every single week. And so you just watch people just hitting trees. But one of the main crashes you see is the person goes over the jump, and if this is the bike, you'd like to land, flat like this. But when you fly through the air, your center of mass, which again is some weirdly defined location. However, would you agree the bike is symmetrical and you are bilaterally symmetrical? So I know it's here somewhere, but I just don't know where. I mean, maybe in the middle of my weight, this way might be around your belly button, but now I got a 30-pound bike below me, so then maybe it moves kind of down to your belt loop. But no matter what you do coming off that jump, that point right there is going to fly through the air in the shape of a parabola. And for me, I think, okay, if I'm going over a double, I want that point to land on the other side of the double, so I'm landing in a downhill position. And so that's speed. If I get the speed right, then that parabola is determined, everything's great. So what if I land where I wanted to land, but unfortunately, we'll say that's the center of mass here. Unfortunately, when I land like this. So then, you go over the handlebars, and that's what most of those crashes are, is people going off the jump and just freezing, and then they start rotating forward, and by the time they land, they're on their head, or the opposite, and then they go through the air and they're like this, and they just land flat on their back, or whatever. But again, that just illustrates why is the center of mass such kind of a key concept. So let's see if we can do it for this. Now, true to what we discussed last time. Did I hit record? Yes, I did. True to what we discussed last time, if you remember, we said that the center of mass, and notice oddly the axes they gave here instead of X and Y are Y and Z. So that's kind of weird, but so, part of me says, well, why don't I just switch that to X and Y so I don't get confused? There's a part of me that wants to do that. But basically what we said the other day is X bar or Y bar was equal to the distance. And again, I kind of don't know whether to write X or Y here. I'll just write something for right now. The distance times, what was the next thing? Wasn't it the area? The distance times the area. And then on the bottom was just the area. And so that was kind of the 2D equation. What do you think the 3D equation is going to be then? Exactly, the volume, because now we're rotating volumes. And let me draw a picture of this so you just kind of go, okay, I see that now. But your guess or your intuition was correct about that. So let me draw a picture of that so you kind of go, okay, I see what you're talking about. So we're just 3D now. Now, as we said before, this particular shape is symmetrical. And so we know the center of mass is on the y-axis here. Does that make sense? So I don't have to worry about that one. But what I don't know is how far is it away? If I draw a side view of this, I'll try to draw a reasonable facsimile of a parabola so it doesn't look like a circle. If this is what it looked like from the side view, yes, I know the center of mass is along that somewhere. But based on what we just saw and based on common sense, we would say it's maybe more down there. Does that make sense? It's going to be a little bit lower because there's more mass on the right side than on the left side. Keep in mind, I'm going to erase this, but keep in mind that what we're really looking for is kind of like volume 1 and volume 2. Those should be equal. I mean, that's how you know that you found it. That's why it rotates around that point, is because you have the same exact weight on one side as you do the other. It's the center in terms of its weight. So that's what we have to do. And so notice the top half or the left half of that V1 would actually be kind of a, bullet shape, whereas the other one would be kind of this, chunk of a cone looking thing. And I mean, the top wouldn't be near as small. I mean, this is almost the same length, but something like that. And so those are kind of, hard volumes to find, but I could just guess and check until I got both of those volumes to be equal. Well, what we did the other day is we took slices and we let rectangles rotate around what we called our axis. Well, this is going to be, again, just for simplicity, I'm going to make this our axis around, I'll say axis of rotation, I guess. It's like we're going to have the shape rotate around that axis. But the key is, what is doing the rotating here? Like what is actually rotating? Does it make sense? We're always trying to come up with this distance thing, this X distance. Now in our case, I'll change that letter in just a second when we make a little bit more sense of this, but does it make sense if I draw a 3D version of this? That since we are deciding to rotate it around that axis right there, that if I were to pick a random location in here, if we were to take a slice of this shape, do you agree that slice is kind of like a little miniature cylinder now? It's not a rectangle that we're sending around, but do you agree that every single, I don't know, dot or particle of that shape right there, they are all a distance of, X away from there? Does that make sense? That's why I have to choose that shape, because all of those are the same distance away. So I basically have to take that volume and rotate it around a distance this time. Do you see the jump from 2 to 3D? Now, because of the way this drawing is done, notice they said, well, actually, that's the y-axis. So in my case, I guess, and again, I'm extremely tempted right now to switch this to X and Y, because that was already kind of a hard part of these problems. And now I'm going to like screw up the letters and so forth. So I don't know, we'll try it. Do you agree with the fact that they asked us for Y bar as opposed to X bar or Z bar? Why did they ask us for that? Well, notice we know where it is with respect to Z. Z is 0 because it's somewhere along this line. So we know Z is 0. What we don't know is kind of how far it is this way. That's Y. So they're basically saying, what's the Y coordinate? So, okay, that actually makes sense. Okay, so then basically to find all of these moments, I've got to take that Y times that volume. Now to get to the location, and this is kind of one of the keys that sort of you need to be good at with calculus, and I find kind of hard to do, but if this is the Z axis right here, and this is the Y axis coming out of here, does it make sense that to get to some point on this graph, remember we're going to let that point go everywhere because we need those slices to go all the way through the shape, that if that's a Y distance right there, then the coordinates of this point right here would be, well, I guess I first go over Y and then I go up and down Z. So that basically means this length right here is the Z, and this length right here is the Y. So I can either let Z work its way from this highest Z all the way to this lowest Z, or I could let Y work its way all the way from this longest Y all the way to its shortest Y. I don't really know how that's going to go yet. But see, what we need now is an expression for the volume of that shape right there. The other day, it was an expression for the area of a rectangle. Oh, that's length times width. But what's the formula for the volume of a cylindrical slice? Does that come back to your brain? And of course, to an engineer, it'd be, Siri, what's the volume of a cylinder? And then you know, right? Like this isn't something you memorize. But a cylinder is just a stack of circles. And since the area of a circle is pi times radius squared, then I just need to multiply by the height of how tall that stack is. So that's what you'd find for the volume of a sphere. Notice R would be in inches. So I have 2 inches, and then height would be in inches. So it'd be cubic inches, cubic centimeters. But the question is, what do I call those in context of my problem? There's no R's and H's in my picture. There's Y's and Z's.
Squared times,
What do you say? YZ squared?
oh, pi z.
Pi Z squared. I'm just gonna write what you say and then we'll talk about it.
I don't know the height, but I guess.
Go
I
for
guess
it.
Times y.
Times Y. It's reasonable. Is that right? Sometimes, by the way, people, when they're trying to figure something out, stare at it thinking, I don't know what to write, so I'll write nothing. Sometimes it's actually easy to write something down and then analyze what you just said and then go, yeah, that works, or no, that doesn't work. Whereas when you're just trying to visualize something that's not there,
Your width or your height infinitesimally small.
isn't the height infinitesimally small?
Like when you have a dy in there somewhere.
Yeah, because I turned it sideways, but isn't our height teeny? Because notice in this picture right here, if this has thickness, then the side of that's at an angle and it isn't even a cylinder. So we got to make it really tiny. Where does that go? You're exactly right.
In place of y.
In place of Y is exactly right. How tall is this? It is in the Y direction, but it's not the entire Y. It's a tiny bit of Y. That's exactly right. What about Z? Can that be, is the radius, is Z replaceable with the radius? Is it right now, or does it still have corrections to make? I mean, isn't that what we just called Z right there? That's the radius, isn't it? So that is right. Z is the radius. So in our context, this is indeed the equation for volume. And so to get a moment, then don't we just have to take that volume times, well, the distance is away? It's actually true. So and on the bottom, I would have the same thing. It's just I don't have that extra distance out front, that distance Y. I'm hoping you see this as similar, but up a dimension from yesterday. And by the way, I don't know how many of you either have to or get to take Calc 4 this summer. I can't believe you can get an engineering degree without Calc 4, but if you have to take Calc 4, the jump we just made right there is the jump that you make in Calc 4. All the calculus you did with me, if you did it with me, was about finding the slope of something in 2 dimensions. Well, Calc 4 is you jump up a dimension, and now you find not the slope of a line, but the equation of a tangent plane. If I said, you know, this is think of this as a ball, I mean, and I said, well, what's tangent at this point right here? Well, that would be a plane now, not a line. So actually the calculus isn't new at all, but you're jumping up an entire dimension. And frankly, you're jumping into the world you've been living in all this time. Like there's not too many things that are 2D. Even a piece of paper can be thought of as 2D, but it's got a thickness. So it's a mind-blowing class. It's really cool. I hope it's taught well for you if you take it. But of course, now that we have this written out, we can kind of let calculus take over, which is, oh, look, I'm in Y land, and that means I need those Z's not to be Z's, I need them to be Y's. And fortunately in this problem, I was told what the connection is between Z's and Y's. I was told how you get one from the other. And so I just need to replace that Z with, well, I guess I have to solve for Z, right? So that'd be the square root of 4Y. Fortunately, the square root of 4 is 2.
You already have z squared. So you can just replace it.
What do I have?
You have z squared in your equation.
Ooh, isn't that even better? Isn't that a good observation? Z squared in my equation, which means I don't even have an ugly square root. So it kind of looks like someone was watching out for us here, doesn't it? So yeah, I can actually replace Z squared with 4Y. So that's even better. And then how's your calculus skills? Do you recognize that constants can be pulled out front? So I could actually pull the 4, which is constant, and the pi out front. So I'm just going to write, because I might be taking too big of a step here for the notes. So if I pull the 4 and the pi out front, then I'm left with 2 y's inside there, or just y squared. And so then I think, oh, whew, that's not a terrible integral. I can take the integral of y squared. I don't have to cheat for this one. And the same would be true on the bottom. Except on the bottom, I would only have just a y, wouldn't I? Now again, we are in y land, which means we have to look over here at this shape and see what values can y take on, because of course we need, if we understand calculus conceptually, we need that little red cylinder to slide all the way through the shape. So we gather all of them, right? We need all the moments. We're going to add all these moments together, of which there are billions. If you let dy be skinny, really tiny, there's billions of them, infinitely many of them. Mind-blowing calculus concept. So, and we don't even have to add them all up. That is really cool. So from this graph, does it make sense? The y values are working their way from the end all the way to the beginning. So I'm going from 4 to 0. Now in this problem, because z was the same, you could have actually screwed it up and still got it right. But so that's of course an important addition if I'm going to continue with this question. And so let's not wimp out, since we can do this integral. Writing things correctly in calculus, the 4 pi comes along for the ride. Once the integral has been taken, which of course is y cubed over 3 or 1/3 y cubed, now you've said the integral has been taken, and then you can evaluate it from 4 and 0. And then the same thing on the bottom, except for it would be 1/2 y squared. Good observation that Caesar made the other day. Does it make sense those 4 pi's actually cancel out? Like you could just, if your goal is not to find each one individually. Now I would say there's a little danger in this, because remember this bottom number is actually the volume, which is kind of cool to know. And if you cancel that 4 pi out, then you sort of don't know what the volume is. But that is kind of a good observation anyway. Let's see, what do we get? 4 to the, I don't think I can pull this off. 4 to the 3rd is 64, but times 4 again, 120, 256, I guess. I think this is 256 pi over 3, isn't it? Maybe I can do this in my head. And then the bottom one would be 4 squared, but times another 4. So that'd be 64, but that's divided by 2. That'd be 32. So isn't the bottom one 32 pi? So again, it's kind of cool that we didn't cancel it out, because at least we know now this is the sum of the moments, if I happen to want to know that. In other words, the desire, how badly does this one thing, I'm going to think about this for a second, how badly does that want to rotate around the y-axis? Watch this up here. Hey, I want to tip this over. Don't think of it as just some nerd trying to tip over a blue bottle, but what if this was a building and it's wind blowing on it? Don't I need to know how much force is required to finally get this thing to tip over? Do you agree that when it gets right here, the center of mass is right over that support on the bottom side? And if it goes past that, and then it's going to go. So can you see that's the job of the engineer, is to understand where the center of mass of this object is? Interesting side note, I built an arbor for my daughter's wedding, you know, just because like who wants to get married out in the open or whatever. But I built the school arbor, and because it was on concrete and we couldn't attach it to anything, it just had to stand there. And it had, just for simplicity, a couple of, am I supposed to separate? Yeah, it's not supposed to. So I had a couple of legs like this, and then connection, and then the thing went up from there. But one of the things I was wondering is, like, what if the wind blows and it gets to the tipping point and actually tips over? Being the person I am, I thought, I hope that happens, because that'd be really funny. And I warned my daughter and the guy she was marrying that it might happen, but I did tell my pastor friend, because I wanted to see how he'd react. But, you know, one of the things, I won't take the time to show you the drawing, but it was a fairly complex shape, and the center of mass of it was not on it. It was in the middle, floating in space. Does it make sense that I had to figure out, you know, how far does this tip before the center of mass is now beyond this point, which is supported? So how many degrees is that? You know, and in this case, it was like, it wasn't very many. It wasn't like 45 degrees. You can appreciate if this has a really long, heavy object on it, that's way tipped over. I mean, it's way back here. It's barely up in the air. It was only like 16 degrees. So then I was thinking to myself, you know, I don't know how wind interacts with it because wind can kind of blow through it. But it was like, how much wind would it take to get it to that place, like the blue bottle, where it's like, oh, you know, it could go either way. Does it make sense? That would be an engineer's job. If we're talking about something like a building, and by the way, that's another amazing advantage to trusses. Does it make sense? Wind's not going to affect us very much. It's going to blow right through it. Whereas if I build this solid, it's going to be a lot heavier, and no wind is it's going to catch wind a lot more. Another side note, just met a buddy for lunch yesterday. Good friend of mine is only 30. We kayak together all the time, and he was in a hole on the South Fork Gorge with his paddle. Paddle blades are about this big, and he was upside down, and the current caught his blade, which is only this big, and he's actually lifts weights pretty solid in the shoulders. Just tore his shoulder right out of socket, and he was janked, and it was anteriorly dislocated, so it was forward, and he was in tons of pain. And that's the same principle. So again, just the stuff is practical. It isn't just some dumb looking, you know, metal shape. So I'm always trying to help you think a little bit deeper about these things. So does it make sense, all that to say, does it make sense that the sum of the moments right there represents kind of the combined energy it would take to rotate that thing in a sense? Now that I have those two things written down, maybe I see that I can cancel pi out of this, and maybe that's kind of cool. And if that's the case, and you know how to divide fractions, this ends up 256 over 96. And of course, no engineer would stop there. Maybe that's the exact answer, and it's real wonderful and everything, but what good does that do anybody? I can't measure that. I can't locate that. Maybe we get lucky and it turns into a nice fraction or a nice decimal, and it does 2 2/3. We sort of got lucky here. And I'll get unlazy and notice, hey, those are meters. And so I should probably say meters. And you should not think you're done. You should go back and look at this and say, would that make sense in this picture? If this is at a distance of 4, that would be at 2 2/3. I think it does. 2 would be right in the middle, and there's no way that's right. So the fact that it's past, this would be 2, this would be 3, this would be, so it's actually saying it's right here. At a glance, does that not appear that just cut that into 2 equal volumes? So it's like, that's pretty cool. It seems to be working. Now, side note just about calculus. Do you agree that, I don't know, I just formulated that based on the fact that I've taught calculus 15 times and I'm pretty good at formulating that. It's not like I had to look at notes. I didn't have to. It's because I'm reasoning about, I see in my mind this disk rotating around a place, and I realized moment would be that distance times that volume. And I just let it, it's not like I didn't look at my notes from before when I did this. They're over here, but I never looked at them. That's kind of what you want to be able to do as much as you can. You can't do it in one pass. Again, I purposely told you I've taught calculus 15 times. I couldn't do this after the first 2 times I taught calculus. I'd have to look at it ahead of time and kind of study and get it back. But you know, your goal is to learn how to think in a class like this so that you can, you know, adjust it to a new problem, not just memorize how to get through something, but that's painful. So that's kind of cool. Let's take a look at one more. And let me see how different it is. Maybe you could make some progress with this yourself before I even start. I don't know. Which one was it? Let's see that one. Notice at least this one is actually 3-dimensionally correct. And again, this is what Calc 4 will look like, because notice it has, and you guys should be familiar with this a little bit because we've done some 3D stuff in here, but notice this is the x-axis and this is the y-axis. Can you at least picture this time looking down on it and how, oh, okay, if I spun it the right way, you know, then y would be up and x would be across like always, and then z is kind of coming towards you. I was looking down at it. That's kind of what happens in Calc 4. And so we could actually find the volume of that in Calc 2 because we could think of it as, well, at least what looks like a parabola here, but then it's spun around in 3 dimensions. And so we found volumes like this in calculus. But notice it says z equals 4y to the 2/3. So this actually is not a parabola, it's some weird shape. As we said before, would you agree that the center of mass is very obviously somewhere along the z-axis? If I draw it to there, and then continue the z-axis down below. It's certainly on the z-axis because of the symmetry of the shape. So for that reason, what did they ask us for? And where is it in the z direction? Because obviously left and right, it's on that axis somewhere. So x is 0. You could say that x bar is equal to 0, and so is y bar, because that tells us where it is in that direction. So the only non-trivial thing is where is it in z. So this is similar enough that I would like you to take a stab at formulating this. The only thing I will quickly draw for you is, isn't this the slice right here that we're talking about? And why is that? Why are we defining this slice right here? Because every one of those little particles are the same distance away from an axis. And so let's rotate this around the y-axis. That'll be our axis of rotation. That's why we're saying if we took a slice right there, what would that slice be? When it was 2D, it was a rectangle. But when you do that here, it's a cylinder. See if you can formulate the integral for this. And what I'm going to do, since you have the paper in front of you, is go back to the previous example, just in case you want to try to do it without looking at this. But if you have to, look at it. Feel free to ask me something out loud. remember, one of the keys to this formulation is all about locating that point right there and understanding that to get to that point, I need to go over, I guess that would be a distance of y. And then up a distance of z. And of course, my YZ point is going to move everywhere along this shape, giving me ever larger radius cylinders. So thanks to that designation, does it make sense Z is actually your distance then? I mean, for the moment calculation, that's how far your slice is away from the axis around which you're rotating. It's a distance of Z away. And the volume formula hasn't changed. It's still this, but what are those called in the context of this picture?
Or it's y.
Yeah, since the radius, should put that in another location. Since the radius was over y, the radius is y. That's exactly right. What do you think h is?
So Doug, this isn't a cone.
No, it's curved. Notice this is not a straight line. So it's cone-like, but it's actually got a curve to it.
So what was this called again?
I don't think it's got a name.
Doesn't have a name?
Because notice that's like a squared equation, but then it's also cube rooted. Remember that's what the 3 on the bottom means, is a cube root. So this is not a typical equation. There's a lot of different crazy curves. Does it make sense that could even be part of a sine wave? I mean, you could come up with any curve there and create a shape that kind of looked like this, but this one doesn't have a name.
So why are we using this formula then? The volume formula?
Because we're still talking about our slice being a cylinder. The key is your slice is a cylinder. I don't even really care what the actual brown shape is. If there was a volume formula for the brown shape, then I'd be using that formula. And so since h is this little tiny height here, what do I call that? Well, z was going up and down, so that makes that then a little tiny bit of z. Remember, that's what d means. A differential element is what a math nerd would say. But one of my top 10 favorite books, which is a kind of an old version of Calculus for Dummies. It's like an 1800s version of Calculus for Dummies. He just calls it a little bit. I love that. It's a little bit of a little bit of z, a tiny bit of z. So armed with all of that wisdom, you could then say that, to say it in the language of this, z bar then would be equal to the sum of the distance, which is z, times that volume, which we just said was pi times radius squared, but radius we switched with y, times h, which is dz. And the bottom is the same, except for minus the distance. We're just adding up those. And the bottom one, do you recognize, in a sense, the bottom one a little bit better from calculus, in the sense that we're saying, hey, let's just add up a bunch of volumes. If I let that thing slide through it, unfortunately, the radius does not stay constant. That's why I have to call it y instead of some number. I'm stuck working with z's. So, fine, but I'm going to replace, like last time, I got to replace y squared. So how's your algebra skills? Can you get that side, the right side of that, to say not 4y to the 2/3, but just y squared? Well, you probably are good with, I can get rid of the 4. People that memorize stuff probably can't do this kind of thing later, but one of the basic rules of exponents is if you raise both sides to a power, then what's true about what do you do with these two powers? If it's a power to a power, you get to multiply them, which turns that into 6/3, which turns it into 2. So now I have y squared equals z squared. You could say z over 4 cubed, or you could actually cube the 4. I think that might save me some trouble in this case. So I'll cube the z, which I can't do, and I'll cube the 4, which I can do. So that would be what I could replace y squared with. And then I'm ready to rip. And what are my limits of integration in this problem? Where does that slice live as I let it slide up and down through the shape? Everywhere from, well, we need z's, right? Z's are in this direction. Everywhere from 16 to 0. You agree with that? And I won't take the time to do the rest with calculus, but again, they were nice to us here. I did not have to be good at integrals. I didn't have to do some trig substitution or some stupid thing like that. I could actually, get this on my own. I hope I have both of these written down so I don't have to take the time to do it. It looks like 256 pi. I better check this, but it looks like the top, if I took the integral, would be 256 pi. Nope, that's the bottom. And the top is 3276.8 pi. Yeah, that's correct. So we get approximately 12.8 inches. So does that resonate as being a realistic answer? Like even if you made a math mistake, wouldn't it be up there close to 16? Since there's not much of the cone down below, but there's a bunch up top, it seems like it'd be like 3/4 of the way up. That seems about right, doesn't it? It's kind of cool.
And the hardest part about Calc 4 was also like limits of integration. That's always the one I struggled with.
Yeah, that
I
is.
got the equation, but I failed on the limits of integration.
Yeah.
0 to 8.
Yeah, and in my mind, it's kind of important to stare back here and go, oh, look, I'm looking at z's. Like I have to talk, z is what's making this move. And so where does z live? What z values do I need? That's my only way of surviving this, because you're right, there's two options here, 8 or 16.
And if you did this around X instead of Y, it's basically still be your radius would just be X then.
That's exactly right. Your radius would be X. You could just replace all the Y's with X's. It just, based on the direction they drew it, where I can actually visually see that as 90 degrees, I picked Y, but you're right. You could have picked X just the same and it would have ended up going away just the same.
Let's say this is like a weird shape in which it's instead of like a circle on top, maybe it's a circle with like shaved off edges on the x-axis. Would you have to do X and Y? You have to rotate around both axes.
Yeah, and that's kind of what Calc 4 is for, because this shape has rotational symmetry. It can be done with two-dimensional calculus. But if you take something that changed as it went up in both directions, then you wouldn't be able to do that. Like let's say you started at the ground with a square, and then you started going up, but then as it went up, it morphed and it didn't even stay as a square. Like by the time it got up here, it was actually a rectangle. So it basically worked its way to there and worked its way to here. I didn't draw that in a very good location. This worked its way to there and that worked its way to there. So it's like working its way up, sweeping up in a curve, and transforming from a bottom in a square, and it's getting narrow as a rectangle. It's actually changing in X, Y, and Z. You actually have to have Calc 4 to find a volume of that, because you have to think of little teeny cubes that working their way through that shape. And so that doesn't have rotational symmetry, and so it's worse. But the good thing is there's not a lot of things like this. However, an airplane wing would be a pretty significant part of our culture that behaves exactly like this. Starts out against the plane like this, and then it works its way out to the end, and it's actually changing shape as it goes. It's not just getting tinier. It's not just shrinking in scope and staying like an ellipse all the way out to the end. It's not like that. Anyway, you got a lot of good examples that I'll post, and I hope you can hammer the assignment and have no problem. But we'll see.